Hello, welcome to Friday morning. It's our last day. We've learned a lot though, haven't we? So we're going to learn a little bit more today. Welcome to the session on solutions for small, rural, and real-world systems. We have several great speakers that we're going to hear from, but I need to make sure you're awake first. So, one quick question. What is a PFAS's favorite song? Forever yours. All right, our first speaker, please make sure that your phones are off. Otherwise, if your phone rings, we're just going to come and answer it for you and make sure everybody knows who it is. Our first speaker is Prasad Galhena from DESOTEC, and he is going to talk about PFAS removal and destruction with the activated carbon reactivation process.
Thank you so much, and good morning, everyone. We've had good talks yesterday, and I really loved Dr. Khan's mathematical modeling course because I used to take one course solving environmental issues using calculus and differential equations. And that was my favorite class in my grad school, so I really enjoyed that. So let's see here. My name is Prasad Galhena, and she pronounced, and I'm with DESOTEC, and we are the largest activated carbon mobile filtration company in the world. We've been in the industry for 30 years, and I'm the applications engineer working with our commercial team. So today's goals, just to give you a clear understanding of, because everybody talks about activated carbon adsorption, resins, and things like that, all the technologies. But as you know, this is a phase separation. So you have something in air or liquid phase, and you got to take it out. So you use activated carbon, and then nobody talks about like destruction. So it's a phase separation, and it's still on the carbon pore structure. So now you have a problem with disposal of activated carbon. So that's what I thought. Okay, I'm going to discuss about destruction of activated carbon after remediation treatment. So my goals here, just to give you a clear understanding of high temperature thermal destruction of PFAS, and plus the byproducts produced in this process, and also to evaluate, because not every single reactivation facility is compliance, EPA. So I'm going to discuss about like how to evaluate and also find the right facility so you can safely dispose activated carbon. So this is the process. You have saturated carbon, and then it's off-site disposal in a reactivation facility. And so during this process, during the reactivation process, the off gas, the flue gas, there's going to be gas emissions and the flue gas salts. And plus reactivated carbon free of PFAS, and it's ready for reuse. A 1-minute crash course on activated carbon, how activated carbon works. So when it comes to PFAS, you can use coal, wood, and coconut shell. These are the three primary raw material used for manufacturing activated carbon. So they all have, for example, coconut shell has a micropore structure, a really high micropore structure. It's ideal for ultra short chain compounds, PFAS compounds, and also for VOCs. Whereas coal base and wood base have a combination of meso and macropores, ideal for long chain PFAS compounds. Depending on the raw material type and the activated carbon type, the absorption efficiency vary. So you need to be careful when selecting the right activated carbon type. Not everything is the same. And this is how the process works. So you have the polluted stream, the liquid wastewater or drinking water stream, and then you have the filter filled with activated carbon, So the liquid goes through the activated carbon filter. All these PFAS and pollutants get loaded onto the pore structure, and you have purified stream. So it's pretty much, this is the basic principle. Of course, PFAS can be completely removed using activated carbon. As you know, it's almost like ND levels, less than 4 parts per trillion. Yes, you can use activated carbon to remove, I explained this micropores and meso and macropores. So that's the mechanism. So the lifetime of the activated carbon filter depends on the type of PFAS and concentration, because activated carbon cannot handle like really high concentrations. So you need to check, like most activated carbon manufacturers and suppliers, they have mathematical models. You can use isotherms and pilot testing to find out that if this is feasible. So that's one thing. And then presence of concentration of other organic and inorganic matter, like especially TOCs in water. It could be drinking water, like in groundwater, TCE, PCE. So those compounds can compete against PFAS, get into the pore structure. And type of activated carbon I explained, and the contact time and discharge limits. Discharge limits, POTW or surface water limits, and you need to be careful with that. The contact time is really important. If you don't provide enough contact time, there's going to be issues and early breakthrough of the filter. So for PFAS, when I design systems, I provide at least 15 minutes of contact time. And if it's industrial wastewater, such as oil and gas systems or chemical plants, stormwater runoff, I design with like 30 minutes to 1 hour contact time, minutes contact time. And this is the most overlooked a piece of technical information in the industry. It's not just activated carbon type, and once you selected your activated carbon type, and now you have a filter and the contact time. But this one, it's called mass transit zone. And so it's pretty much, let's say that you are introducing water or air from the top of the filter. And so there is an absorption front that moves through the activated carbon bed. And you need to have like a sharp, short, a very efficient absorption front or mass transit zone. So when you design a system, the length and the rate of the mass transit zone depends on the flow rate, concentration, temperature, contact time, and especially when it comes to vapor phase application, humidity. So these are the parameters. It's not just activated carbon, and this is an engineering solution. So most engineers, I've seen that they need like 2 filters with 2,000 pounds of carbon, or 10,000 pounds of carbon. It's not just activated carbon. You need to design the filter properly with enough contact time in order to adsorption to work. So keep that in mind. This is a comparison of 2 mass transit zones. The blue ones, it's short and it's sharp and it's very efficient, and it moves through the bed, which is designed properly, no channeling or anything. And as you can see, the red one, it's pretty much like the broader, a large mass transit zone, because it's not enough contact time, or it's not enough flow rate or something like that. So this is the this shows that it's not just activated carbon. It's about engineering the system as well. I think you can see this one. So this is the interim guidance on. So I'm going to talk about like thermal destruction from hereafter. So interim guidance on the destruction and disposal of PFAS, and this is the 2026, the newest interim guidance, and it talks about activated carbon is one of the best available technologies to remove PFAS, and then it talks about like the thermal destruction of activated carbon using multi-earth furnaces. As you can see, the contact time inside the thermal reactivation kiln, and also it promotes a RECTRA certified or permitted facility to reactivate the polluted activated carbon. So this is really important because, as I explained at the beginning, there are few reactivation facilities in the US. Most reactivation facilities, they don't have RECTRA certification in order to accept hazardous activated carbon, like spent activated carbon. Some kilns are running around like 1,400, 1,500, but when it comes to PFAS, it's mandatory to maintain at least 1,700 Fahrenheit. So as you can see, here it says that 1625 to 2400 Fahrenheit. So these are the guidance given by EPA. So when it comes to thermal reactivation process, so there is the reactivation kiln has especially multi-earth kilns, and there are like two types: multi-earth kilns, those are vertical ones, and horizontal rotary kilns as well. So it maintains, three zones. The first zone releasing moisture and impurities, and zone 2 releasing heavier components like hydrocarbons and things like that, and zone 3 high temperature to create new pores, especially with steam injection. And once it's reactivated, and the carbon is cooled, sieved, because during the reactivation process, and the carbon becomes brittle, and there's going to be like a loss of like 5% to 20% due to burn off. And now you need to screen all these the fines and small particles, and then it goes through a quality control and ready for refilling. One thing that I'm going to discuss this one, but when it comes to carbon quality, so it's important to test the reactivated carbon quality before refilling of filters. That's an important piece. Iodine numbers, there are ASTM parameters such as moisture, butane, iodine numbers, things like that, to make sure that it's in the proper levels, the pore structure. And then this is the most important part, because as I said, this is a transfer phase separation, and once the PFAS is destroyed, at DESO during the thermal reactivation, the PFAS molecules needs to be completely destroyed, which means that turn them into acid gases, CO2 and H2O. So in that process, it's important to have the flue gas treatment. We call it as APC unit. So post combustion of gas, and there can be a scrubber system, and also there can be like bag houses, things like that, to remove these particles during this off gas treatment process. So and the most important thing is the reactivated carbon has a footprint up to 13 times lower to virgin carbon. So the customer doesn't have to use virgin carbon every single time. They can reactivate and save some money on carbon filling. This is a schematic of a kiln. This is how the temperature profile inside the kiln. And as you can see, there is an afterburner. It's typically the reactivation kilns can run up to like 1900 Fahrenheit. 1900 to 2000 Fahrenheit. And also there can be afterburner to completely destroy all these hydrocarbons, PFAS, things like that. The afterburner can run up to 1900 to all the way to 2400 Fahrenheit. So the recycling, this is how it works. First, 120 degrees Celsius, drying the saturated activated carbon, and volatilize, low boiling points components. That's around like 450 degrees Celsius. Pyrolysis of other organic components up to 600 degrees Celsius. It could be like PFAS, things like that. And steam injection for oxidation up to 950. So when it comes to steam injection, it's not only oxidize, certain molecules inside the activated carbon pore structure, it also create, certain like new pores. So there's not going to be like a big difference between properly reactivated carbon versus virgin carbon. So this is why the heat profile is very important. And so during this is, I always go with the EPA protocols. So the PFAS destroyed at, I should say, around 1625, 1650 Fahrenheit with proper residence time, depending on the kiln type. It could be 30 minutes to 40 minutes to all the way to 8 hours, especially those rotary kilns, horizontal kilns, and it takes about like anywhere from 6 hours to 8 hours to reactivate one single bag, like 1,100 pound bags. Also required oxygen-rich conditions for breakdown, especially when you inject steam injection. The destruction efficiency, this is the most important thing. It could be more than 99.99% with validated stack testing and destruction testing. The byproducts during the reactivation. So as I explained, the PFAS is dissolved and then completely destroyed, and that create inside the post-treatment of flue gas, the scrubber system, it produces HF and SO2, and the scrubber system handles this one by injecting sodium hydroxide and caustic to neutralize completely, and then in the stack, there's going to be only H2O and CO2. That's pretty much so. And emission control and byproducts, again, for flue gas treatment, you can use thermal oxidizers, acid gas, scrubbers are used, byproducts, HF, CO2, H2O, trace inert ash. And then laboratory analysis is important because you got to test the stack test and any trace inert ash or residues and things like that. It's important to test those things to make sure that those are free of PFAS. And also the reactivated carbon, this is another important factor. Once the carbon is reactivated, you need to make sure that the carbon is free of PFAS residues. So you can send samples, or in-house laboratories can run this one to make sure that it's free of PFAS. Selecting a reactivation facility, it's important to see that you can read that interim guide on PFAS reactivation, spent carbon reactivation. Number one, ensure permits to handle PFAS-laden spent activated carbon, whether this is a permitted facility, a RECRA facility, and things like that. And I've seen many things in the industry over the last 15, 16 years, and the supplier says that, yeah, we can run PFAS, but actually they are running around 1,100, 1,200 Fahrenheit, and so it's just that these are PFAS and releasing into the environment. It's mainly because there is no permit for that kiln facility. And third-party destruction efficiency data, especially stack test data, and make sure that because you are transferring your liability to another facility, and you need to make sure that you're not going to get sued by like EPA or any other government body. So make sure that third parties data is available to make sure that it's completely free of PFAS. Process certificates, once it's been reactivated, there has to be a process certificate. You send out 10,000 pounds, and now you have 7,000 pounds or 8,000 pounds reactivated carbon. That's the process certificates. And verify operating temperatures and emission controls. You can do a site walk. You can go to the facility and make sure that you do an audit of that facility for reactivation. And clear chain of custody of waste profile document. That's pretty much you're transferring your waste into another facility. Life cycle benefits of reactivated carbon reduces demand for virgin activated carbon, because each time when you use virgin carbon, as you know, last few years, there was a really high demand for virgin carbon, and the prices are going high, especially due to tariffs, especially carbon coming from other countries, gonna get 30%, 40% tariffs. and cuts greenhouse gas emissions and long-term disposal risk. Each time when you reactivate, you don't have to send it to a landfill or somewhere, and you can completely destroy all this PFAS and use that carbon back. Hazardous to non-hazardous, so hazardous carbon, it's filled with TC, PC, PFAS, and turn that into a non-hazardous compound, and you can reuse that. Especially at DESOTEC, we call it as circular economy. So you use it again and again, at least 5-6 times before it's completely exhausted. Limitation and considerations. Not all spent carbon is suitable for reactivation because the facilities might have restrictions, especially the scrubber system or caustic pump, and it could be the maximum PFAS limit. So before you send out your activated carbon laden with PFAS, make sure that the facility can handle that. There has to be a document and by a permit or their destruction data, and this is the maximum PFAS level that we can handle. And short chain PFAS may require enhanced controls. We have different types of activated carbon for that. Like I explained, for short chain compounds, ultra short chain, you can use coconut shell. When I design systems, I use maybe 2 or 3 carbon types, maybe 2 different stages to remove TOCs and short chain PFAS, and then long chain. Reactivated carbon must be tested post process. Of course, it's a lab analysis to make sure free of PFAS. Limited number of reactivation facilities in the US, so the logistic would be kind of complicated. So you need to make sure that you cover that. I think that we're gonna, this is DESOTEC. Yeah, thank you so much, appreciate it.
Thank you. We're going to leave all of the questions to the end. So next, we will bring up Phil Farina from Clear Creek Systems, and he's going to talk about PFAS treatment for rural water treatment systems.
And I want those extra 3 minutes.
Nope, we're not going to give them to you.
Good morning, everyone. My name is Phil Farina, and I'm with Clear Creek Systems. And the first thing I want to do is I want to ask a question. How many people here either represent a rural water community or work with a rural water community that has a PFAS problem? Throw hands up. So I got 1 member of the audience. Who cares? Okay, that's good. We all can. What I'm going to be talking about today is a roadmap for rural communities. At the end of the day, we're going to try to provide a practical guidance roadmap. These are things that a rural community can do step by step by step. There's a lot of noise in this industry. There's a lot of smoke and mirrors in this industry, and there's a lot of fact in this industry, but it's very, very difficult sometimes to separate fact from fiction. So our goal is to try to help you understand by following a specific series of steps from beginning to end. Will give you all of the things that you need to do in order to develop a treatment system, because that's the ultimate goal, is the development of a treatment system. We're going to talk a little bit about the importance of PFAS treatment, but we've all been down the PFAS road before. We all know all of the things that are bad. We all know all of the issues that are involved. So I'm not going to spend a lot of time on that part, but it's really important to understand that we do need to treat this material. There are some facilities I've talked to that said, this is going away. I speak to the EPA once a week. It is not going away. This is something that they are going to be continuing to process. And then we're going to talk a little bit about the challenges that are facing the smaller rural communities. So we're going to go from contamination to cleanup and provide a course to get from point A to point B. Paid commercial announcement, Clear Creek Systems is a PFAS treatment technology agnostic company. We treat all kinds of water, and we have utilized 35 years of experience in developing water treatment technology that allows us to bring this concept to the table. This is not something that we developed in the last 2 years. We've been utilizing all of our knowledge and technology to help develop this roadmap to treatment. So, per and polyfluoral alkyl substances, our best friend, PFAS. We all know it's the forever chemical, and there's a lot of disputes about what that really means. At the end of the day, it means the following. Most things break down in the environment. PFAS doesn't. The reason it doesn't is the quality of the chloride or of the carbon-fluorine bond. That bond is a non-naturally occurring bond, and because of that, it is incredibly strong. Because of the strength of that bond, microbiology cannot break it down because it costs too much energy to break it down, as if you were eating celery for the rest of your life. The nutritional value of that celery is not sufficient for the microbes to survive. Therefore, they prefer other carbon sources. It's as simple as that. I'm a microbiologist by training, and believe me, I wish my little babies could do it. They can't. It is toxic. What does toxic mean? Toxic means it has an impact on the biological system itself. It does not mean it causes cancer. There is not a single peer-reviewed journal entry that indicates that PFAS in any of its forms causes anything. There is correlations, but not causation, and that is incredibly important to understand. Why does it matter? We talk about why it matters. It matters because it is persistent and it's bioaccumulative. The Journal of American Medical Association last week had an article out that said that 98.8% of the people in the United States have PFAS in their blood right now. 98.8% of the people have PFAS in their blood right now. Where is that coming from? It's coming from your food, your clothes, your air, your shampoo, your mouthwash, your toothpaste, this carpet, the air. It's coming from everywhere. But we're focusing on water at this point in time. It does have some level of health risks. It is correlated with maturity. Women, young girls are becoming sexually mature earlier. It is correlated with that. But so is 35 other things. There's a significant amount of hormones in our drinking water. If hormones are causing early maturation, do we not think it may be coming from the hormones in our drinking water and not from the PFAS? So science is not definitive, and it's important, again, to understand that. Environmental presence, literally it's everywhere. It's easier to list the places where it isn't than it is to list the places where it is. Regulatory and public response. People ask me constantly, why is this a big deal? It's a big deal because we made it a big deal. It's important to understand that biologically, this material has been around since the 1940s. We still do not understand all of the biological impacts. So it's important to continue to do research. It's important to continue to study this material. What are we trying to do? First and foremost, we're trying to hit with regulations. And the first series of regulations that we promulgated out was to set enforceable standards of PFAS in drinking water. That took place in April of 2024, and that was the first national primary drinking water regulations that was ever promulgated by the US EPA. US EPA is not an enforcement agency, it is a regulatory agency. They are regulators, they're not enforcers. They are putting it out there for the states to do the regulation. Next step we're trying to do is reduce. We're trying to reduce waste. We're trying to reduce the waste streams. And DESOTEC and some of these others that are doing destruction technologies, that's part of where they're fitting in. Industrial landfills and biosolids. Anybody aware of biosolids? Tremendous source of PFAS in our environment. Absolutely unbelievable. What are we doing? We're targeting sequestration. What is sequestration? Very quickly, sequestration prevents PFAS from going out into the environment. If we take the PFAS, put it on a media, take the media, put it in a drum, take that drum, put it in a landfill. That landfill has a liner, a leachate collection system, and a PFAS treatment system within that liner. We've removed that PFAS from the environment. It doesn't go back into the environment. Destruction is one way, sequestration is the second. What are we developing? We're developing destruction technologies, and destruction has to be the complete disassociation of the carbon-fluorine bond. No daughter products, no sister products, no repolymerization products. Very, very, very difficult with this material. There's always something that is left over in the destruction process. What other contaminants are produced? You know, H2S is produced, fluorides are produced, F2s are produced, F3s are produced, fluorine gases are produced. There's a lot of things that we have to deal with, not just let's break the bond. Chemistry is chemistry. Things have to happen. I'm going through this really quickly, and I really apologize. This is part of a 2.5-hour presentation that I give for the EPA. So if anybody's interested in the real presentation, let me know. Regulatory framework. There are 2 sets of regulations. First regulation is the non-drinking water regulation. Is anybody aware what the non-drinking water regulation is? No, good, because there isn't any. The US EPA has not said anything about non-drinking water at this point in time. They are working on that. And what is non-drinking water? Non-drinking water is things like remediation, stormwater, construction dewatering, CCR ponds, all of these other things. No regulations right now. States have regulations. 9 states in the United States have eliminated the utilization of biosolids as a land application product because of PFAS in it. We're building mountains of biosolids. Non-drinking water regulations, they have not established anything. The states have primacy on that, so they're working down that path by the state. Some states have levels of like 70 parts per trillion for non-drinking water. Some states have levels of 4. So if you are in a state that you're working on a wastewater treatment facility, please contact your state regulator and find out what their specific regulation is. What's next? The US EPA is going after landfills, POTWs, pulp and paper. All that wonderful shiny paper in front of you, that's got PFAS in it. All the inks that you're dealing with, that's got PFAS in it. PFAS is going to be added to new air permits. We're not having enough trouble with handling it in water. Let's just really complicate it and start handling it in air. It is not a hazardous waste. It is a hazardous material. That's hugely different. And again, I can spend hours in telling you the differential between that. And some of these Superfund sites, those poor guys that got their nice little closure document, may have to reopen it if they're leaking PFAS out of that facility. Federal drinking water standards. Everyone's read this. 284 pages, April the 10th. Everyone read it? Yeah, I did. The standards are PFAS at 4 parts per trillion for PFOA, PFOS. You have the 10 parts per trillion for Gen X and all of these others, and the compliance deadline of 2029. I have had people come up to me on a number of occasions and say the compliance deadline is not 2029, it's 2031. How many believe it's 2031? Excellent. January 6, 2026, the U.S. federal courts threw out the request for vacate. The reason they threw out the request for vacate is predominantly because in order to change the law, it's a legislative change, not a judiciary change, and because of that, the EPA backed off. It is 2029 that we need to be in compliance with these drinking water standards. Say again? Correct. He's absolutely correct. So everyone who's waiting, please stop. Because you're going to have a hell of a time trying to get all of these things in on time. I'm telling you right now. State of Florida. State of Florida has mandated under US EPA Region 4, they are complying with the federal regulations. There's 5,500 systems under the rule. And so far, 34% have reported testing. What are we waiting for, folks? We're running out of clock time. The date for compliance testing is April the 14th, 2027. It's less than a year from now that you have to have your reports in for compliance testing. Rural site challenges. You know, one of the things about rural facilities is they tend to be small. So you don't have a lot of people to deal with. You don't have a lot of revenue coming in on the water stream. So revenue is a big factor for rural communities. Large municipalities have large number of people. They can charge 2 pennies or penny to treat, and they have lots of revenue coming in. If you've got 2,500 people, you can't raise the price enough to cover. So that's one of the important factors, is very small populations and very limited staff. Most of these smaller facilities have 1 or 2 guys, and some of them are not even operators. They're just Joe Farmer who comes in on Tuesday and checks the system. So compliance is going to be stepwise at that point. Aging infrastructure. A lot of these small facilities that we see, they're old. They're basically a well in the ground, a pump, maybe a filtration system, 99% of the time no, and sometimes a disinfection system. That's it. That's the whole thing that these small rural communities are dealing with at this point in time. Most of their source water is groundwater. Groundwater is different from surface water when it comes to contaminants and treatment. And it's really important to understand, when we get to the map, the difference between groundwater and surface water. Basic treatment limitations: most of these facilities don't have a building. It's really small. It's just a well outside with maybe a shack over it. That's the whole deal. So what do we do? Let's start looking at the map. So how do we develop a treatment methodology? The first step we want to take a look at is sampling. Data. Please, if you are designing a treatment system, do not do it without data. Do not guess that carbon is the answer. Do not guess that ion exchange is the answer. Do not guess that fluorosorb is the answer. Data. You have to do this anyway. You have to do the comprehensive analysis anyway. So that information will lead you down the path. That's your first step to getting to a treatment system, is data. So compliance sampling. There is a very specific set of compliance sampling that have to be done. I don't have time to go through that today, but it's very, very specific. Sampling frequency and compliance is going to be based on your specific permit within the state of Florida. They have very specific compliance requirements. Make sure you understand what those compliance requirements are. EPA approved analytical methods. There's lots of methods out there that are coming. You know, there's one that can tell you down to 1.5 parts per trillion for $100 in 15 minutes. Okay, guys, right now, today, where we sit, US EPA is 537.1 and 533. That's drinking water. That's what you need to be utilizing. 1633 is for something completely different. It's not for drinking water. Make sure that you are utilizing a certified testing lab. Very important that the labs are certified. This is the analytical that you need to perform. At a very minimum, all of those under the UCMR 5 have to be tested for. And lithium. Why lithium? Because we're throwing away a boatload of batteries. What do you think the EPA wants to know about lithium for in batteries? Is because down the road, what do you think the next thing they're going to be regulating? It's lithium. So you need to know that going in. You also need to know all of these other things. Why? When I show you the rest of the map, you'll understand that all of these things may impact your water treatment technology. If you have high nitrates or sulfates or TSS, it's going to impact your treatment choice. What are those treatment technologies? Right now, there's 2 major classes of treatment technologies. There's the media systems and the non-media systems. Media systems include our friend granular activated carbon. I am a firm believer in bituminous, virgin carbon. It has the best application for PFAS. It has the right micelle size, etc. All right, you can use coconut. It may not last as long. You may not get the net result. But at the end of the day, that is one of the materials to look at. The other one is ion exchange. Ion exchange has a different mechanism. It's much faster. You may use less media. It can be a few dollars more expensive, but over the life of the system, it may be less costly. When you're calculating how much this is going to cost, do not look at the instantaneous cost, but look at the 3-year total cost. And what you're going to do, and I'll show you the math in a minute, is you're going to look at the total cost, divide that by the amount, or divide that into the number of gallons of water that you treated over those 3 years, and you will get a price per gallon. And that is a critical value that you need to know. Fluorosorb is another media application. For non-media, we have reverse osmosis. We all know the problem with reverse osmosis. It takes all the salt out of the water. It changes the taste dramatically. You have to put salts back in and make the water taste, and you lose 25% of your water. Not a real great plan for drinking water, but it can be accomplished. Nano and ultrafiltration, Florida loves this. It's a really good technology. It does work really well. And then foam fractionation, which is not compliant for drinking water. So I put that up there for anybody who's got a landfill or wastewater treatment facility. Foam fractionation may be something that you can do. That is my granddaughter. Selection criteria. Hey, you got to have family involved, right? Treatment technologies. When you're looking at your system, before you design your treatment technology, you want to have that information that I just told you about when it comes to the analytical. Really important to have that analytical before you start looking at treatment technologies. So you want to know what your PFAS profile is. What do I have? I have long chain, short chains, lots, little, contaminations, etc. You want to know that before you get going. You want to cost and scale considerations. You don't want to put in a massive system for a small amount of treatment, okay? So it's really important to be working collaboratively with someone, not just give me your lowest price, because I tell you what, how many would agree with this statement? The lowest price on the bid is not necessarily the lowest cost of what I pay at the end.
Can I jump up and down?
Okay? That's what I'm saying. Guys, we have to get sensible on this kind of thing. Technology preferences, that is going to be determined by the media, not by the media, by the contamination, what you have. If you have all short chains, DESOTEC would agree, carbon is not necessarily the media to go to if only thing you have is short chains, because it's not the best media for short chains. So again, make your decision based on data, not on preferences. This is a very busy chart, but what it basically says is there is a known profile for each of the different methods and medias that you want to utilize. Now, I usually spend 15 minutes just on this slide to help you understand all of your parameters, but suffice it to say, there is enough data to help you understand which methodology you should be applying to your treatment system. What are the tools? Everybody needs to understand that you're not alone. There are tools that will help you define your treatment system. And that first set of tools is the Rapid Small Scale Column Test. Everybody calls it the RSSCT, which is correct terminology for it. And what the RSSCT does, it allows you to look at multiple medias to help you determine which media will exhaust first. Now, people want me, people want me to say that, it's going to tell me how many weeks or months or years or decades my media is going to last. It doesn't. What it will tell you is this, in a line-by-line comparison of GAC, Fluorosorb, ion exchange, whatever medias you want to have, it will tell you which media will exhaust first, second, and third. It will not tell you how long it lasts. There is a mathematical equation called the Thomas equation, which is incredibly complicated, that will utilize that information and give you a number. It's a mathematical number. It's not a guarantee or a warranty. But this will help you define what treatment you can look at for your system. Your other tool is the pilot study. The pilot study can take upwards of a year because you have to go through the 4 seasons on a pilot study. With an RSSCT, you really don't, because all you're trying to figure out is how long will this media last against another media. It's qualitative, not quantitative, whereas a pilot study could be quantitative. You can actually see over the course of a period of time how long a media is going to last. But guess what? We don't have the time anymore to do that. We've run out of time because a lot of people didn't do it earlier. Okay? So 4 steps in defining your treatment system. And again, I apologize for the speed of this, but I only had 25 minutes. First step, consider the water source and it's what it's going to be used for. If it's a drinking water source, groundwater, or surface water, those are different waters. If it's a wastewater source, if it's stormwater, you want to know that before you start going down a path of determining what your outcome is going to be. You also want to look at the water analysis. Remember we had that long chart? That is critical. You need to be running that analysis. By having those two data points, you're halfway to a choice of what you're going to do. Third data point is understand the treatment levels. If you're drinking water, we know what those are, 4 and 4. If you're wastewater, your state will have a different set of applications. So we're not just talking about drinking water today, we're really talking about water treatment. If you follow this step for all sources of water, you will get to a treatment system that works. Step 4 is your key considerations is your installation. Is your installation permanent or temporary? Everything is based on flow rate. If you're using a media, if you're using a reverse osmosis or even ultrafiltration, flow rate will determine things like size, footprint, cost, media volumes. It's incredibly important to know your flow rate. And what happens frequently is someone says, oh, on Tuesday, we're 1,000 gallons a minute, but every other day we're 100 gallons a minute. I'm not going to tell you to build a 1,000 gallon a minute system. Because if you do, it's going to cost you hundreds % more than you need to spend because you need to balance that out. Okay? So collaboratively work with people. Please stop the give me your best price scenario because you're never going to get there with that, honestly. What do some of these systems look like from a design and implementation? Everything should always be with a media, a lead lag treatment system. That's really, really important. Okay? Carbon uses the largest footprint. Ion exchange and Fluorosorb use a much smaller footprint, predominantly because of antibed contact time is way, way faster. Systems can be fiberglass like the one in the previous slide or carbon steel like this slide. Cost of treatment, this is the money slide right here. On a 1 million gallon system, 700 gallons a minute, you've got a cost of about $1.8 million for equipment and installation, not including a building. You got $1.8 million in equipment. Your annual cost to operate that equipment, including media changeout, is about $145,000. In 3 years, you add those all together, so it's 145 times 3 plus 1.8 million. You get $2,100,000. That is a lot of money for a small community. I get it. But at the end of the day, you're also treating 1 billion gallons of water at the end of 3 years. You divide those two numbers, you get 0.0019. That's doable. There are ways to get to that point. It is very, very doable. Word or two about destruction. We're not there yet. Lots of things going on. I can't spend any more time on destruction. Money. There is a bunch of money available. The US EPA's got money. USDA's got money. There's NAPOLS has money that is, it's all free money. All you have to do is apply for it. And if you want to spend some time on this, please let me know. I can spend a lot of time on helping you find money on this. What do systems look like? Real quick, I got 4 slides. This is a treatment system that can go up to 50 gallons a minute. It's under 100 grand, completely installed, operational, and ready to go. Comes to the site, all you do is plug it in. The 2 gold pipes, you plug in the top one, you plug in the bottom one, you're operating. Drinking water, this is a 500 gallon a minute treatment system, $165,000. We can put them in Connex boxes, we can put them in sheds, we can put them in anything that you want to put them in. So at the end of the day, last slide, I promise. Water treatment is a science, not a commodity. Science does not lend itself to the lowest bid. I've said that 5 times. The lowest bid solution is frequently not the lowest cost. When developing a system, you should focus on understand the water, collaboration, agree on a clear, measurable, prioritize your outcomes, and consider the life cycle costs over the initial costs. If you need to get a hold of me, that's where I am.
It's always hard to stand up here, especially for people that give talks for all the time. Because we'll take talks that are 7 hours and try and put them into a half an hour. and you feel like you're speed dating. Couple of things you said, before we go on to the next speaker, I want to reiterate, because it's really important. Everything that you see out in the news, there was one that just came out the other day that started talking about the EPA pulling back those 4, they're going to create a rule to pull back those 4 additional PFAS and the hazard index. understand that that's already codified in the Safe Drinking Water statute. So in order for them to pull that back, the court system's actually going to have to find a procedural issue with that to pull it back. Because otherwise it falls under the anti-backslide rule, and they've already lost that in court twice. So don't rule out those PFAS yet. Because you're gonna see them eventually, and there's already people in Congress that are trying to codify it congressionally, so it can't ever be pulled back. So that was one. Two, the life cycle cost that he talked about, that is hugely important. When I'm dealing with clients, I take them out 10 years so that you know how to budget for 10 years. Because at 10 years, it includes everything, whether a media needs to be changed out, everything. And then three, when he kind of breezed past testing, go out and read the testing methodologies, please, because something as simple as sunscreen on your hands can throw your test off. So please make sure that when you're doing the testing, you read the testing methodologies. So, okay, our next speaker, we're going to switch gears here. We're going to go from the drinking water side here to remediation. So Paul Hatzinger is the Director of Biotechnology Development and Applications Group at APTIM, and he's going to talk about PFAS, bioremediation, inherent limitations, and future prospects.
Very good. Thank you, Tonya. Let me start by saying this is not your solution for small drinking water systems. Please don't propose bioremediation at this point. So what I'm going to do is I'm going to talk to you a little bit about microbiology. I know we have at least one other microbiologist here, and I'd like to just provide a bit of an explanation about where we are in terms of looking at the biodegradation of these types of compounds. And I'm going to start off talking about our perfluorinated compounds. So those are the ones that have fully fluorinated backbones. And we're going to, at the end of this, I'm going to talk a little bit about precursors and what's going on with precursors. And these are our, PFSAs, perfluorocarboxylic acids. These are the compounds that are regulated, so these are the ones that we're concerned about. But first, we're going to do a little biodegradation primer. So why are bacteria degrading these things we put in the environment in the first place? So I'm sure many of you as consultants and regulators have looked at various compounds like BTECs. So what organisms do with many of these compounds is they use them as carbon sources and electron donors, just like when we eat a hamburger. Same thing, right? They form biomass and energy. They don't get big and fat. They divide. They make more of themselves. Thank God we can't do that. And as electron acceptors, in this case, they're using oxygen. So this is why when you go to a site that's a BTEC site or a PAH site, a lot of times you have to do biosparging or you have to get oxygen into the ground because that's what they're missing. The other thing we've learned over 30 or 40 years now is that bacteria can use things like chlorinated solvents as an electron acceptor. So in this place, what we do is we put carbon in the ground. This is where we've used things like emulsified oils or other, you see all these vendors have different carbon substrates. We add the carbon to the ground. There are bacteria there that will use that carbon. You create anaerobic conditions and they can use compounds as electron acceptors. There's also some organisms and things like for explosives and nitrosamines and things, they need other nutrients, nitrogen, phosphorus, sulfur. And there are actually some organisms that use polyfluorinated PFAS as a sulfur source. So there is some precedent here for some of the PFAS. And then finally, there's these reactions that are called co-metabolic. I see James Mills sitting there. He's done some of his Ph.D. work on this type of thing. And there are organisms that actually have these broad specificity enzymes, and they can degrade lots of different contaminants, but they gain nothing from the process. Okay, that's called co-metabolism. All right, so with that primer, let's talk about chlorinated versus fluorinated organics. So we know that we have a long history now with chlorinated solvents. We know there's this organism called Dihalococoides. There's another one called Dihalogenamonas. They use acetate as a carbon source and hydrogen, and then they dechlorinate things like PCE and TCE, ultimately through to ethene. We understand now the genes that are involved in this. We understand the organisms. There's hundreds, probably thousands of papers on this process, and I hope many of you have applied this at chlorinated solvent sites over the past generation or two now. Okay, why did this occur? Well, chlorinated compounds have ancient origin. And this is something that, I've sort of come to learn, and over time that there are thousands of chlorinated organics in nature. We don't think very much about this. And there are enzymes that create these. And here's, a nice example of a compound that commonly occurs in nature. It's made by red algae, and you can see it has chlorine and bromine on the structure. And people have looked at this compound actually as an anti-tumor agent. So it's made by red algae. And there are a variety of other compounds, and often, there are algae and other organisms that make these as a defense mechanism. So we've got, chlorinated, brominated compounds in nature. So what's happened is over the millennia, bacteria have evolved to use these compounds, and so we come along, a very short time ago compared to how long bacteria have been here, and we start making things like PCBs and PCE and TCE, and well, guess what? Bacteria have a framework already because they're used to a lot of these chlorinated compounds being in nature. So an organism like Dihalococoides that we think, wow, it just suddenly appeared to degrade our chlorinated compounds, well, it didn't. It actually, in nature there are already these compounds, and this organism probably had some natural substrates, and we just made its life a whole lot better by putting these types of compounds in the environment. All right, so let's take a look at fluorinated compounds. There are natural fluorinated compounds. There are not a lot of them. So fluorine is the 13th most common element on the planet, and yet there are only a handful of natural fluorinated materials. So they're very rare in nature, and the other thing is they're usually monofluorinated or occasionally difluorinated. What you don't see in nature are the types of compounds that we made that have this long backbone with completely fluorinated carbons, right? That's a very different animal. So here's just one example. Here are some other examples, and what you notice about all these different natural fluorinated compounds is that there's typically one fluorine. One of these that's very interesting is fluoroacetate. Now, fluoroacetate is natural. It gets taken up in certain plants, and it's one of the common causes of large kills of cattle in places like Africa or in Australia, because if they get grazing on the wrong plants, those that hyperaccumulate fluoroacetate, it'll kill them. And I had the fortune to go to New Zealand this year, and was sort of walking along in New Zealand. They're very particular about, they have possums that have now invaded New Zealand and some other small mammals. And you know what they use to kill those? They use baits of fluoroacetate. And they will show you, in certain areas where they've used these. So a little aside there. And people always say, bacteria can't defluorinate a compound. And that's also not true. Bacteria can defluorinate compounds. We've known this for a long time. The first enzyme that can do that was 1965. So there are natural defluorinating enzymes. But again, looking at monofluorinated compounds, and we've known, remember chlorofluorocarbons. That was our other fluorinated compounds that we've had big problems with, in the past 50 years or so. And there were papers in the early 90s showing bacteria could defluorinate some chlorofluorocarbons. So that's possible. That's a super strong bond, yes, but bacteria can defluorinate that, again, when you have a monofluorinated compound. The problem is we come along with these, starting in 1947, with this long fluorinated backbone. Bacteria do not have basically the infrastructure to deal with that. So we've created something new that is, then again now becomes very persistent. So we heard a little bit about thermodynamics yesterday. So the next question becomes, in nature, if you can gain energy from something, then generally organisms will find a way to do that. So when we look at Dihalococoides, it can take hydrogen, it can oxidize hydrogen and reduce PCE. And for those of you who are engineers, you understand this, I'm sure, very well, but then you get a positive energy gain, or what's called a negative delta G. So you can combine these reactions. You don't need a microorganism to do this, a reduction reaction, an oxidation reaction, and you can see if there's an energy yield from that reaction. So if I make up an organism, we'll call it Difluorococcus. Is it possible to do the same thing with these types of compounds? So can you take PFOA, for instance, defluorinate it to octane and fluoride, and have there be an energy yield? So if we take a look at this electron tower, and this is something where you look at reduction potentials of different compounds. And at the top, we have our really good electron acceptors, and at the bottom, we have our really good, we'll say, electron donors. So we use oxygen as an electron acceptor, which is great because it's really one of the best that there is. As you sort of run down that line, these electron acceptors become sort of less and less positive, so you can gain less energy from a reaction with those. But if you look here at TCE, you'll see so for the reaction from PCE to TCE, that's a pretty good electron acceptor. DCE to vinyl chloride is a pretty good electron acceptor. So where do some of these fluorinated compounds fall on this chart? And the fact is, at least with the fully fluorinated compounds, they fall all the way at the bottom. So it's almost impossible for a bacterium to couple the oxidation of some common molecule and reduce one of these compounds. There's just not an energy yield to do that. Well, it's not impossible for it to do it if it puts energy in. It's impossible to do it and gain energy from the process. You cannot grow by those reactions. Okay, more good news. Fluoride is toxic. There's no use within a bacterium or within us for fluoride for the most part. So if an organism takes in fluoride, and a lot of them do, you have to have a specific transporter to remove that fluoride. Okay, so let's just switch to the other side now. So is there any hope? Is there any hope in the future for biodegradation and bioremediation? And I would say that if we were having this talk in 1980, 1979, we were starting to deal with chlorinated compounds, and some guy would be standing up here and say there's no hope for biodegradation of chlorinated compounds. And you can go back in the literature and you will see that, actually, if you go back to those eras. So is there any hope for this? Okay, so I've just told you it's very hard for an organism to grow on PFAS, so what about a couple of other things? What about non-growth reactions? I talked about co-metabolic reactions, so is there some way that organisms or enzymes can break these things down without energy yield? Or can cells potentially use some energy in the process to break these down? So one example of this where cells use a lot of energy is nitrogen fixation. So, nitrogen is really valuable for bacteria, for us, and most of us can't use nitrogen from the air. The air is 70-some-odd% nitrogen, but you can't use it. So some bacteria have evolved enzymes where they put in a ton of energy. These are cyanobacteria, rhizobium, bacteria that grow in association with plant roots. They put in a ton of energy and actually fix nitrogen down to ammonia. And this is really, really important. And in fact, if you go back before a couple of Germans named Haber-Bosch figured out how to do this chemically, natural nitrate, natural ammonia were very, very rare commodities, and we were importing materials for fertilizers, et cetera, from places like Chile where there's a lot of natural nitrate because we couldn't make things like ammonia very readily. Okay, so as I go into some of these studies about PFAS biodegradation, I'm going to give you first a cautionary note. And a great man named Carl Sagan said, extraordinary claims require extraordinary evidence. So you're going to start seeing claims of biodegradation of these materials, and there's a number of papers coming out. Secondly, look at what the researchers are looking at. I see a lot of papers come out, I get sort of excited, and I realize they're looking at a monofluorinated compound or they're looking at a precursor. They're very different animals than these perfluorinated compounds. Many PFAS strongly sorb to media. Disappearance is not extraordinary evidence, okay? And I've seen a number of papers that have either been retracted or brought back because things like PFAS, if you work with them, they absorb, even in bottles, you can take PFAS and you can put it in a serum bottle and you can shake it up. And if you just try and take subsamples, you're going to have very, very poor recovery. So you have to do things like complete methanolic extractions of those samples. Very, very important. So if you start looking at this sort of thing, think about what compounds were they looking at? Were appropriate controls used? Are there mass balances? Do pathways make sense? And then you start looking at evidence of biodegradation. Okay, so this paper came out in 2019 from Princeton, a gentleman named Peter Jaffe. He's an old school microbiologist, published in Environmental Science and Technology, and it basically said, I have an organism, a Pseudomicrobium species, strain A6. It biodegrades PFAS and PFOA. This created a lot of discussion, let's say, and then a few years later, a correspondence came out from a bunch of other scientists, and they said, back up just a minute. I'm not sure that and this is one of the best journals in our field, I'm not so sure that this is actually occurring. There was some controls we're not sure about. You're using this iron compound that may sorb PFAS. So what's going on with this organism? What is this organism? So it was not isolated with anything to do with PFAS. It's actually was isolated from a swampy area, and it was to study a process called Thiamox. So this organism oxidizes either ammonia or hydrogen, and it reduces ferrohydrate, so it reduces an oxidized iron compound. That's what it does for a living. Long before PFAS became an issue, my laboratory is right by Princeton, and I've known Peter for years. We took this organism in our lab, and we were looking at dibromoethane, EDB. And it debrominated dibromoethane, and it does TCE as well, by the way. And he started looking at it for PFAS, just because PFAS became all the rage. He'd been using this organism for years. Now, interestingly, the organism, does it have any enzymes that could do this? These days, you can sequence a bacterium basically in a matter of hours and look at all the genes that are there. And a gentleman at Minnesota named Larry Wackett has been working with this bug. It has some interesting dehalogenases. It has a fluoroacetate dehalogenase. So it has enzymes. It has a fluoride transporter. It has some interesting enzymes that potentially could be involved in defluorination reactions. So that's a check in the box. Do you find it in nature? And the fact is, people start looking, you do find this organism in lots of different places. This acidomicrobium that's very, very closely related to this one. And I don't know if they've yet seen activity in another organism besides his species, but you do find it in different regions. So that's pretty interesting. So here's some data. This is published now. This is data from Peter's lab, but essentially what we're looking at are on the bottom here, we see PFOA down to PFBA, so decreasing chain length. We see this of incubation from time 0 to day 100. And we see declines in all of these compounds except PFPEA. It didn't seem to have any activity. And on the positive side, the other thing we see here is we see increases in fluoride for some of these compounds. Now, fluoride is fairly hard to measure. You have to be careful about how you're doing that. But that being said, we're seeing loss of compounds. We're seeing increases in fluoride for some of these compounds. So that's a good check in the box. We're seeing, at a minimum, we're starting to see a fluoride produced. Another study where we're looking at daughter products, and in this case, essentially you're looking at PFOA declining over 60 days, and you're seeing the production, and the important compound here, I don't know if I have a pointer or not, but anyway, don't have a pointer. So you see this HPFOA. So what seems to happen initially is you're taking one of these fluorines off at that alpha carbon, right? And the other thing that's kind of interesting with these compounds, if you can get a fluorine or two off, they become much more biodegradable. They become much more reactable in different types of systems because you've got this very stable structure with all the fluorines. If you start picking those off, then these compounds can start to break down. And you see a bunch of shorter chain daughter products as well. And there are some pathways proposed where this can occur, and you do see the same type of thing with some fungi for precursor type compounds. Okay, just sort of the last study. So then you say, well, yeah, but could it be biostimulated? This is a pure culture. And this was one last experiment where essentially they took some aquifer materials from an acidic aquifer. It likes acidic conditions. And they added the medium that you can use to grow these. They added ammonia, they added ferrohydrite, and they added either PFOA or they added PFAS. So F1 was PFOA, F2 was PFAS, and then they had some sterilized controls. And essentially, so you see losses of both of those. You also see growth of the A6 type organism, and you see increases in fluoride concentration. So this bacterium, again, giving those substrates, it's not growing on PFAS, it's not growing on PFOA, but it seems to be some type of co-metabolic reaction where in fact it's using its growth substrates and it's got an enzyme that's defluorinating these. So pretty interesting evidence, and there's several papers out now by this group. So just in summary, it does seem to be widespread. It doesn't grow, but it seems to be able to defluorinate some of these. Is it getting all the way through to, just carbon? It seems to be going down to shorter chains. It's not going all the way through, it doesn't appear. But very interesting organism, and at least some initial precedents now to some biodegradation for these compounds. Other things that people are looking at, peroxidases and lactases. These are fungal enzymes primarily, but we also produce some of these. Plants produce some of these types of enzymes. like the peroxidases, they tend to be extracellular or lactases. Fungi have to break down lignin, they have to break down trees. So again, these stable structures are something that people have looked at. And this is a place where you're looking at in silico design of enzymes. Can we design enzymes? You know, we're in this new era that can break these things down. Now, there's more and more papers coming out. I mentioned the Jaffe work because I've reviewed a lot of that. I start looking at new papers, and I want you to see slide 18 again. Go back, look at what they've looked at. Do they see daughter products? There's a lot of disappearase papers out there right now, but there's more and more in the literature, which is encouraging, but all of this stuff sort of needs to be followed up on. Okay, now I'm just going to wrap up with precursors. This is a very different story. There's a lot of bacteria that transform, we're going to say biotransform, not completely degrade or mineralize these precursor compounds. And we've seen various talks over the last 2 days where people have looked at things like landfill leachate and other materials, or you've looked at oxidation reactions, and it's these precursors that are transforming, and that can be interesting, and it can also be a bit problematic. So what happens is when you have these AFFF sites, you have a lot of precursors there. And as I think was mentioned yesterday, you know, we can't detect them all individually. You use either a total organic fluorine method or a total organic precursor method where you take a sample, you oxidize it to things we can detect, and you see what's there. But you have a lot of these precursors, and some of them have long end groups, and they tend to be bound up in the soil materials in an aquifer. So one of the questions is, well, you know, what kind of happens to these over time? And the ones that you guys would be looking at, you know, that you see in like 1633 or things like 6.2 FTS, 8.2 FTS, we see a lot of those. Well, in fact, there's good precedent for bacteria that can actually biotransform these type of things. And this is just an example. And this was also an example of organisms that can use some of these compounds. If you limit the environment in sulfur, there are bacteria that will, and this is repeated many times now, will actually use the sulfate group on the end of some of these compounds as a sulfur source, so they can cleave that off. And then there's a co-metabolic reaction. This was one of the papers from our group in ES&T, and essentially we looked at organisms that grow on things like methane and propane, and in the environment they can take 6.2 FTS, they have some oxygenases, they put an oxygen on there, and there's a couple of different routes they go. The problem is what you're ending up with are shorter chain carboxylic acids. So you're going from kind of something that you know is there or don't know is there to things that you do know is there, and that's kind of the big problem, is we're not getting all the way through. So when you look at some of these fire training areas, and again, these sites are difficult, they're challenging to look at, but when you have a source area, a lot of times you have a lot of these precursors around. You also have biological activity occurring. So you have bacteria that are taking some of these precursors and they're slowly changing them to things like perfluorobutanoic acid, some of these short chain carboxylic acids. So you have a continuing source. So you can look down gradient and say, okay, you know, I have these compounds, I've got diminishing numbers, but you have to account for the fact, or in the vadose zone, you may have these other sources, and they're going to be transforming to carboxylic acid. So over time, you may have sort of increasing concentration of those based upon conditions if you look at a site. And with that, just a quick summary to close out. So a lot of these precursors biotransform, but they transform to PFAS. And there are some interesting organisms coming along in enzymes. Wait and see. I don't think this is going to be the ultimate solution at most of these sites. I don't think we're going to find the halicocoides, and that has to do with energy considerations and other things. But that being said, you know, I'd love to be proven wrong here in 10 years where most of this session is about, you know, bacteria that are grading PFAS in the environment. So I guess we'll wait and see on that one. So thank you very much.
I'm glad you gave that talk instead of me. I don't think I could have made it through all of those names. Next, we're going to move on to soil remediation of PFAS using rapid leaching technology. I got introduced to this yesterday. And this is one of the talks that I'm really excited to hear from. So let's bring up Bryan Massa and Shaun Malin of HRP Associates.
Good morning. Everybody okay? Still on the bus? All right, I got a thumbs up. I recognize that this talk is between you and your refill of coffee, break, snack, and all that stuff. So we're going to keep it high level. We're going to have a little bit of fun here. As was said, Bryan Massa is my colleague here, companion, travel partner, anger translator for me. So if you all get unruly, I heard this was a rough crowd, so I brought in a little bit of backup this week. We're here to talk about soil remediation, which this is my first time at the forum. I appreciate the group here. I understand the conferences have been awesome. I see that I believe that we're the only soil remediation discussion this week, so I'm excited to bring this to you guys. Before, with everybody kind of being burnt out, I know we've been at this for 2 days with some really high-level science. When you guys walk out that door in 20 or 30 minutes, this is what I want you to understand, is that rapid leaching technology is simply a massive volume reduction. We have excavated piles of soil stockpiles at base up in Pensacola. I've heard from multiple of you. We all know that there's soil stockpiles up there with AFFF in it. We excavate the soils, whether it's from Milcon projects, restoration projects. So we take hundreds of thousands of cubic yards of dirt, and we put that into an RLT cell. We'll show you how we construct it and things. We fully saturate that cell, we flood it, so we convert all this dirt into a smaller volume of water, a couple thousand gallons of water. And then also in discussions with a lot of you, I want to be very clear that we are water treatment solution agnostic. Okay? I'll keep Bryan from having to translate for me. But in our particular research during our R&D, we did use foam fractionation. So this cartoon signifies that transformation from all that mass to a highly concentrated drum of foam fraction concentrate. I'm going to do something really stupid here, and I'm going to shuffle my own slide deck willingly here. I'm going to show you how to construct, just real quick, we're going to show you how to do it. Bryan, unfortunately, has to listen to himself on video for 2 minutes here. Let me see if I can get this going with the button.
Dual-purpose remediation technology that can be used to actively dewater saturated sediments extremely fast, allowing you to not use cement kiln dust or other additives. It's also
Can you all hear that?
Treatment technology that's able to mobilize contaminants from a solid state into a liquid state and allow those contaminants to be treated in a treatment train process. So what we have going on here is they're actually starting to build a cell. We're going to use this one for dewatering purposes for sediment, and this can be an extremely cost-effective technology by allowing you to dewater rapidly without the use of additives and allowing processes to get shipped to landfill for disposal. The technology uses multiple layers. First, it starts with site preparation. They build a bermed-in area out of soil. Depending on what you're looking at, this particular site's not have any concern with contaminants, so we're not using a GCL, which is a geosynthetic clay liner. Again, it's clean sediment. This is just for dewatering purposes. So it has a filter fabric underneath it. That's the base. That protects the geomembrane, which is what you're looking at now, which is a plastic liner. The fabric basically keeps any sharp objects or anything that may be under there protected from the liner. Liner goes on top of it. It gets seamed in place, which is what the crew is doing now. This 8-inch drainage line, perforated pipe that goes through the liner. What they're constructing now is called a boot. A boot is they're physically melting the liner to the PVC pipe to make it a complete watertight bond. They'll continue building this aspect to it, and then after this, they're going to install a drainage layer. The drainage layer is a proprietary patented layer that we've developed to allow the rapid dewatering to occur. That's going to be the next step, and then after that, the product is ready to use and get loaded up with soil. The liquid in the soil rapidly dewaters out of this pipe, comes out the other side. This side drainage pipe allows for about 1,500 gallons a minute, so it can dewater quite quickly. If the water was contaminated, you'd do treatment on the end of it. We would be collecting it into a secondary pond, and then that could go through a wastewater treatment plant process. Typical for PFAS, if PFAS was a contaminant of concern, we'd be doing foam fractionation, ion exchange resin, granulated activated carbon, and then we'd be using the water to reintroduce it back into the cell and wash the contaminants out again.
We're back here in Middletown, Connecticut today to...
This is the
run some
demonstration
time
of how
trials on our
fast
work-in-progress
we can
drain.
leach out of
It's
this
called
cell.
the whip drain. The whip drain utilizes our rapid leaching technology to dewater sediments and soils. Today, we're going to be applying between 20 cubic yards up to potentially 60 cubic yards of a sediment mixture of sand and loam and saturating it and then seeing how quickly we can dewater it for remediation purposes.
So for PFAS soil, imagine that we've excavated soil, we've put it into the cell, and we've filled it with water. I want to note for most types of materials we get, after 24 hours, we have the material down to an 8% moisture content, which for most DOTs is the green flag to load up and hit the road. I just want to reemphasize, if you didn't catch it, this particular cell was built for a dredging scenario for a client in the Northeast. So there are some of the patented components that I'm going to talk about here momentarily. Were not part of that construction, so you didn't see it, but you'll see it in the field demos here. All right. So, in essence, now I know why everybody's looking at this TV, because we all need glasses and we can't see that far, can we? All right. In essence, that cell that you saw constructed there is watertight. I want you to picture kind of a two-drawer dresser, if you will. In the top box is where we're loading the soils that are impacted into the cell. We're going to fill that cell up with water, fully saturate that cell. And then we have all of the tiramisu of the geotextile liners, the things that you saw in the video that were getting constructed there. We have an air component to it, which I'll show you on the field demo, that agitates and creates the partitioning that allows the PFAS go into their natural state, if you will, wanting to be on that air-water interface. And the agitation moves the dirt around, which is kind of the upsell on a traditional soil washing method. I would explain that most soils, most types of soils are dry, air quotes, in 24 hours. In that second bottom drawer of the dresser is where we collect the leachate, and we pump that off into a water treatment trailer that we have for field demonstrations. But obviously, as I said, we are agnostic, and we can plug in the water treatment train that is most appropriate given cost, client needs, concentrations, type of contaminants in the water as well. This is, again, a significant cost, a significant mass reduction, and we are really half the cost at worst for a lot of a traditional dig and haul for most East Coast facilities. We'll get into a cost analysis here. It's important that you did see the drain running out in that dredging scenario. We have a closed loop system, so we're green. We're recycling the water. If we have to do, depending on the influent concentrations in those soils, if we have to soil wash multiple times, we're continually circulating that water through that treatment train. All right, so how do we design the process? You guys say, we're in, let's talk about it. The first step is we have to come out and grab some preliminary samples to perform laboratory bench scale testing. So you guys have soil stockpiles, or you have an area that you want to excavate source material out. We'll come out and we'll collect soil samples, we'll analyze them for typical properties, grain size, concentration, in and out, and we roll that into our bench studies. That information that we obtain from the bench scales then goes into our field pilot, gives us a lot of data and information that we need to figure out how many rinses we think we're running into the, through all the different washes given the type of material. And then obviously from that we come up with a full-scale design. I have here a collection of different laboratory bench scale tests. This first one that I want to talk to you about, I know it's probably hard to see in the back, but this was early on in our R&D. We had an airport client that had their hands on some military spec AFFF, so we created our own sample. The starting concentration for that sample was 5.5 ppm, so pretty hot. It was a 50-50 mix of ChemGuard and Ansolite, if I'm saying that second foam. And there's a variety here on the x-axis. We were tinkering with pH early on in the R&D. What we found with this particular soil material is that a neutral pH of 7 with 3 rinses got us 94% removal, and so that was the proof of concept we were looking for at this point in our R&D process. A second standard, we employed a laboratory to create a 1633, as in EPA method, 1633 standard. That entry-level concentration was at 175 ppb, so significantly less than the AFFF proof of concept. Again, with a pH of 7, we got about 90% removal on that as well. So we have can you do it with high concentrations? Can you do it with low concentrations? We're answering those questions here. We recently were given the opportunity to go to an Eastern North Carolina base that you've all, if you've fallen asleep on the couch, you've seen their commercials, their PR at night. And we were given access to come collect some soil samples from one of their source areas and do an in-the-field DOD. It was a firefighting training exercises. Again, we went through that first phase of R&D and came out and grabbed some samples there. You can see that again, we had 89% reduction on the 1633 list. Again, running top analysis and running 1633 to try to understand what precursors we had in those materials. After one rinse, we had 89% reduction on that one. This is, so then moving out of the laboratory bench phase, figuring out the pH of the water that we may want to use, understanding the concentrations, understanding the material that we're working with here. We then go to the field and we have these mobile demonstration units, which are basically mini-size 1 cubic yard boxes that have the same geosynthetic liner system in there. You can see in this particular box, again, for moving from a dredging scenario to an environmental remediation scenario, you can see the air component that we've added into the bottom of the box. Again, I want to emphasize that that air is part of the secret sauce that put the soil in there to agitate, and actually not unlike a foam fractionation system here. You see a lot of controls. We have a pump skimmer here. Compressed air goes into there. It's a watertight design, and of course there's an effluent drain line here. I got a quick video here to show you what it looks like. There is soil in there. I know the water looks kind of black in this particular video, but this is soil in the box with the aeration component. And you can see the foam. We're refoaming the foam. So we're rinsing the soil grains. There's agitation going on in there, and we're creating a micronapple, and we're skimming that off on a surface pump, which is kind of at the bottom of the screen there, that green piece of equipment there. So we run that for a couple of minutes. This again is the draining component of it. So we determine how many rinses we need to do to get to the desired concentration. Our limitation on the effluent is limited to the size of the bung on the outside. So as you saw that huge pipe on that first video there, we're not joking about the rapid dewatering. This is what our Eastern North Carolina pilot looked like. We had lots of finds. So that was a challenge to kind of design that in the field. On your first rinse here, it's probably a little bit hard to see from there, but we had our general Guinness consistency on the first rinse. We had lots of foam in there. We had very high concentrations that we were dealing with there. I think we went through 6 rinses for the purpose of this demo. given the concentrations and the data that we received through the lab bench scale testing. You can see that it's really not foamy on the last rinse there. So at the end, moving from the lab phase to the field phase, especially on the DoD installation, once again, we removed 96% through rapid leaching technology. So what you have here is whether we're dealing with AFFF concentrate with the mil-spec sample that we created, or a low-level soil concentrations, maybe that you find downgrading of a source area, or maybe IDW that you're collecting through RI investigations and so forth, to an actual source area there. We're pretty much in the neighborhood above 90% PFAS removal using this technology. Now again, to be clear, all of these tests were proof of concept. We wanted to show people that this technology worked. There are a variety of different ways. We're anticipating funding to go to the next step to try to take that 95% removal to 99.9% removal. We're also watching DoD and EPA move forward in what the risk assessment process is going to look like. You know, we can collect SPLP on the back end of these rinses. Again, we've rinsed this material 6 times. So we can have conversations with the regulatory agencies to say, you know, yeah, there's a little bit of concentration left that's above soil standards or protection of groundwater standards, but this material's been rinsed 6 times and it's not coming out. And so we're ready to have those conversations, those types of risk assessment concentration. This is actually a cool photo of inside the foam fractionator. Kind of looks like this, that brittle kind of cookie that your mom used to make around Christmas time. Don't recommend ingestion. And so at the end of the day, wrapping up a little early here for Q&A, the difference between the standard soil washing that I think most of you have seen on DoD through research grants is, again, that air component and that agitation and the full saturation that we get in our cell. So again, we're not standing at the top and watering material down like watering your yard. We're literally filling that cell, and then we're agitating that material, so we're getting 360-degree saturation around those material particles to ensure the PFAS leave that grain. We rapidly dewater, so it's not like we have to handle mud on the backside of this. We recycle the water. Again, we handle large volumes of water due to the technology in the liner system. And again, not advocating one particular technology or not, but utilizing the foam fractionation is really kind of, or some other destruction type water technology is part of that sauce, getting from the huge volumes of soil that many of you are working through with your clients on trying to figure out how to get that to a meal or get it to a Subtitle C in Michigan, Nebraska. We have a little cost analysis here. This is a particular scenario that Bryan was costing out for a client in Massachusetts. Lots of the East Coast facilities have to travel far to get to a Subtitle C if that's the determination that the client makes and that the regulator makes. This was a Massachusetts site, 35,000 cubic yards. This is hard to see, but you can check it out on the slide decks when they come out. Essentially, what you see here is a lot of capital investment to build an RLT cell. But what you see by the end when you get down there is the T&D and the transport and the digging and the excavation and the trucks on the road and the truck traffic and how many weeks it takes to take that volume of soil there really shakes out. We're about 88% less expensive than T&D from Mass to Subtitle C in Michigan in this particular example. Obviously, the cost analysis for this technology is dependent upon a variety of different criteria, how close you are to the certain landfill, whether you live in a state where Subtitle Ds with leachate systems is acceptable, and all that stuff's in flux. I've heard, we've all been talking about it this week, right? So as we continue to evolve, we like where we're sitting here. We're having lots of discussions with DoD. We've given lots of quotes to private side clients. I don't know what you guys are experiencing, but a lot of our private side clients are kind of in a hold pattern, waiting to see how things shake out. Obviously, as regulations evolve and things come out in the news, stops, all those kinds of good things. And that's it. I told you, I didn't lie to you. Kept it high and simple there.
technologies like this are going to come even more into play as CERCLA shakes out. Remember that under the CERCLA ruling, PFOS and PFOA containing materials will be listed as materials for hazardous transport. Nobody knows what that's going to look like yet. We haven't fully seen those regulations yet, but it will significantly impact the cost of transporting impacted materials. So with that, why don't we open the floor up for questions?
For the last speaker, you mentioned soil. Has this been tried on biosolids?
Okay, you've got a, there you go. Yes. It's coming.
Testing? The question was biosolids? Yes. We have many clients that we've talked to about biosolids. It's something that we're looking into. We believe that with a couple of tweaks that we can handle biosolids, but we're working through the opportunity, the funding, and you know, we have some good ideas on how we would deploy that.
For the last speaker too, great talk. What about deconning? After you get done with the equipment, and do you have how difficult it is to decon the piping and everything, or do you just throw that out?
That's a good question. I think in essence we foresee this technology being deployed for a long period of time, right? And again, I know I'm kind of hammering on the DoD front, but we're installing these at bases where potentially there's restoration. For those of you that work in the DoD world, the remedial investigations are still ongoing, and they've extended the time period, and they've run out of money. And so I think that in the DoD space, RIs are going to go on forever. So there's going to be IDW generated for years on end, and that's, you know, kind of material at an X volume for here and there. You know, this technology on the liner system, if you saw some of the HDPE plating, this technology was deployed in the oil and gas field for frac sand washing, and it's bulletproof. They drive heavy equipment on it. You can beat these things up. Some of these systems have been in the field for 10 years now and are working full speed. So in theory, you could build one of these, utilize it for X volume, and then tear it down. But in general, the utopia, right, would be to install it at a particular facility where you had a significant amount of soil that you were generating for multiple projects, a construction project, a lot of hangars being built with soil grading. So I guess I'm kind of tap dancing around unintentionally. The decon is not something that we've given a lot of thought to, because we see them as kind of longer term solutions for the sake. Is there anything you want to add on that?
I mean, I would note that the components are HDPE and geocomposites, and to decon it, we would use the same concept where we would drain the cell and we would wash all the materials, wash the PFAS residues off them, and run it through a treatment plant and just continue before we decommissioned. But I think what Shaun said is our hope is that a system like this would get mothballed. So you would use it for a particular construction project, mothball it. When a new construction project starts, you do it again, and you just keep reusing it. So that's how you drive your price down. You have your large capital investment, but you can continue using it.
Any additional questions? Up here?
Hang on one sec.
I apologize, I'm kind of new to this, but I got a question for the DESOTEC gentleman. What kind of testing are you doing to validate the 99.99% destruction?
Yeah, that's a great question. So, so we do stack test as well as that any residues. I cannot publicly mention, like honestly, what test that we are running, but it's a third party and it's runs by Alliance Group. That's the third party lab. So we collect like, off gas, samples, as well as that dust and particulates, coming out of our scrubber systems, and we test both solids and air samples. And it's the source testing for hydrocarbons and VOCs, and plus PFAS as well. Yes, correct, yep. It's, I guess that it takes about 3 months or so. Yeah. Thank you.
Good morning, great presentations. Questions for Phil. For the upcoming reporting requirements in April 2027, what's the distinguished factor for large systems versus small systems?
There isn't any. It's across the board. It's the same reporting structure, but each individual state has a specific reporting structure for that site's permit.
Okay.
So when the permit is issued for that site, it will tell you the specific reporting requirements. Initially, it could be as frequently as 4 times a year until such time as they get 4 samples with non-detects, and then it goes to twice a year, and then it's every other year. But once you have a breakdown in the detection, then you may have to go back to 4 times a year. But because of groundwater seasonality, because the groundwater comes from a different place, if it's traveling through a PFAS contaminated field, and it rains in the spring but not in the summer, it's just that seasonality piece that comes into play.
Right. So I guess typically municipalities are testing once or twice a year, but I saw quarterly.
On average, once they get past the quarterly test with 4 non-detects or less than limits, two less than limits,
Yeah.
then you can go, again, it depends on the state and the permit for that particular facility and the amount of water, where it's coming from, all of that. It's very site specific.
Okay. I had one other question for HRP folks. So, we've done soil washing for chlorinated solvents and so forth, and it tends to be a total mess. This looks much more. Clays and organics are always a challenge, right?
Your microphone's breaking up to us up here. I'm not hearing you clearly.
He's asking about, I think he's asking about soil types, right? And if clays and organics work for you guys differently than regular soils?
So, fantastic question. We get this question from everybody. The pilot study that we actually did had significant amounts of clay and produced significant amounts of fines. We're able to deal with that. So for this particular scenario, we had wasn't a full frac tank with weirs, and it was just a regular frac tank, but we put a sequesterer inside of it, and we're able to get the particles to drop out, and then we put it through cartridge filtration before it went through the system. We were able to change the geotechnical properties of the soil by adding a very coarse well sand. So I think in this particular situation, we did maybe like 10 or 15% of the well sand acts in aggregate, and we ground that into the material, breaking up the clay that allowed us to get the removal. And during these rinse cycles, Shaun didn't jump into like the full-blown into the weeds, but we grabbed samples of clay balls out of each rinse cycle, as well as the regular material, to see if there had been any difference in concentration. Were we seeing higher levels of PFAS in the clay, which is what we would expect, versus lower stuff inside the more sandier material. And what we found is when we did the initial breakup of the material, we were getting the water to actually flush through all of the clays into the porous areas and wash it out. So I think the answer to that is yes, we would use some sort of aggregate mix to break up the clays. Obviously, it works better in sand. If you have a sandy material like I have on Cape Cod, you don't have to add anything. But this particular pilot, we were like 50% clay. It was tough, but we were able to deal with it.
So do you have to break that clay material up? I mean, we have a lot of clay in Florida, especially superficial, central and North Florida. So would you maybe have to run it through a pug mill or something to break it up?
I think if we were going to do this full scale, we could go a combination of something like that, or we could go with like a bucket auger mixer that has like the spikes on it and actually kind of grind up the material together and add in a mix. That would be something that I think we would do during like our bench scale study stuff, where we could try mixing different aggregates, which is what we kind of did here. We found that a fine sand was no good, made the stuff too almost too clay. If you went with like a pea stone, that didn't work good either. But a very coarse, angular well sand worked perfect. It was enough where it would grind the material up and give us that. So going full scale, we would probably either go with a mill like you were talking about, or with a bucket auger mixer.
And a follow-up question for the HRP. So it sounds like you're using air sparge as your mixing mechanism.
Yeah, so what we're doing is we're doing large bubble aeration, and we're not trying to promote foam fractionation inside the cell. The foam fractionation sort of happens naturally because PFAS wants to be at that air-water interface, but we're actually just using the large bubbles to agitate the soils and mix it around.
Okay. And on your cost comparison, it sounds like you're about $250 per cubic yard?
Even less than that. So for that particular one, I want to say we were in like the $150 a cubic yard. But what happens is you have you have a large initial capital investment. So that particular scenario was 35,000 cubic yards. If you mothballed the system and you go to reuse it, say you have another project and now you have another 35,000 cubic yards, you've already paid for the equipment so all of a sudden your cost goes from 150 down to what the labor cost would be, and you're probably half of that. So the more you use the system, the less expensive it becomes to process the soil.
Okay, thanks. And I had a quick follow-up question for the DESOTEC. On the analysis, how many actual individual PFAS compounds do you test for during your reactivation certification?
That's a great question. So that depends on the customer requirement, the carbon that we receive from a particular site. For example, because our sites are RCRA certified, so we cannot blend activated carbon like from one site to another site. So we have to run like that carbon from that site in one kiln. So let's say that if there are 8 or 2 or 3 or 40, so we got to run that. So that depends on the customer, I should say. Yeah. And we also have developed our own method, like similar to SW846 EPA method. So in Belgium, so our company is based out of Belgium. So we have our own PFAS leaching test method that we developed. So that's going to be probably going to be the POP regulation in Europe. So it's either equal or better than EPA test method as well. So that's coming up, and we are trying to work with EPA right now.
Thank you.
Thanks.
Sure. Thanks for the talks. I had a quick question for Phil. For those of us that are working in the world of helping to deploy EC SDC funds and looking at all the installation of small water systems that's going to go on here for the next 2 or 3 years, one of the concerns is what happens after those systems are done and they're handed over to those local folks to operate. What have you seen in terms of any success stories or any thoughts on how to best help those folks learn and help to maintain those systems so that we're not back there 3 to 4 years again to do a whole new system?
Yeah, that's very appropriate to this body today. Working collaboratively with your engineering company or your system designer or your manufacturer is going to be a continuous step-by-step process where we tell you what the equipment is, how the equipment works, what the maintenance is, how things are going to happen. The beauty of PFAS treatment systems, if you're using a media type of a treatment system, they are incredibly simple. It's water going in, going through the media, water coming out. Okay? As long as you're operating it correctly, as long as it's designed correctly, as long as you don't have hiccups, then it pretty much operates itself. A lot of the systems that we have put in have been in mobile home parks. And let me tell you, there's not a licensed operator running at a mobile home park. They're in a trailer somewhere, or they're in a tough shed somewhere, and literally once a week someone comes in and makes sure there's no leaks, and then once a month someone takes a sample, or once a quarter depending on the permit requirements, and that sample gets set out. But we also have services for, if someone has a question or a need or something like that, your designer or your builder, will have services available for you. The name of the game is by dealing collaboratively as opposed to give me your best price. Because when you get the give me your best price scenario, your support structure may not be there. Because they're just giving you a very low price structure. So you want to deal with people that are in this business long term. And those of us who are in this business long term have the capacity to help train, inform, and support those smaller facilities. Because it's not that complicated. Does that help?
I'm going to add to that a little bit. Work with your local rural water associations. These are associations that are designed to work with small systems that will have circuit riders that come around as well to help them. State agencies will also have registries of what they call non-transient, non-community operators that are willing to come in for a small fee, once a week, a couple times a month. Or you can actually, there are many services out there that will actually offer, if the state is requiring a licensed operator, you can actually sign a contract with somebody that will come in and sign off as the licensed operator, coming in once a month or whatever's needed for that particular system. But the state agencies will have actual lists of licensed operators that are contractable, and so will those rural water associations. Any other questions?
Yeah, great talks. This question is for HRP. Since we're learning that PFASs are more volatile than we previously thought, have you put a dome over your pilot or bench scale testing to validate that you're not losing any PFASs in your air as you push air through the systems?
Very good question. So there is a modification to this system where it has a cover on the top of it that pulls a vacuum to address that. I think we're still doing R&D on these sites to see if those are issues, but that's something that we would be evaluating as well, as we do know volatile PFAS is an issue, and the design for this does allow for a retractable cover with a vacuum pull on it, so you could run it through an air scrubber.
That's very wonderful. So you're working on completing a mass balance?
Yes. When we did this testing, this particular round, we did mass balances on the water and soil end, and we were able to correlate that data very, very closely for what was in soil, what was leaving. But the next step would be looking at that volatile aspect end of it as well and seeing if that is an issue or not moving forward.
Wonderful. Is this data publicly available, or I can just...
It is not. Okay. This data will eventually become a white paper. We need to, as Shaun had said, this is at a DOD facility. So this might be something that you guys will find, maybe in the next 5 or 6 months or so as a comprehensive paper that has significant amount of analytical data. We collected all samples with top analysis so we could see how our technology worked with the precursors, and it has mass balance calculations in it as well.
Great question.
Hey, I had a question for HRP as well. Apologies, it's hard to see the details of the capital cost comparison table. So just, I guess, elaborate on that. It looked like you presented that you have an 88% mass and cost reduction when you compare capital costs of just T&D versus the construction and treatment of the soil through your process. But the scenario looked like a dredging scenario. So just in general, did that cost reduction include addressing the now contaminated water that you have, whether it be management through a wastewater treatment facility or foam fractionation of the water itself? Does that cost reduction include addressing the water as well, or is this just a cost reduction in the dredging scenario?
Nope, it's everything. So that cost comparison, and hopefully you'll be able to see it better when the slide deck comes in. We looked at every aspect that would affect the cost. So that included excavation of the material, loading the material into the cell, operating the cell, the cost for the water, the cost for the treatment aspect to it, and then the cost to remove the soil from the cell and then put it back. In this particular scenario, the soil would be washed, cleaned, and then actually brought to a subtitle D landfill for daily cover usage. The second scenario included the scenarios you would expect for an excavation project. So it was excavation, loading it into trucks, sending it to subtitle C landfill, and then providing backfill. Both had backfill options to it too. So we tried to be as thorough on the cost comparison as possible to show that there is significant savings. It's just the cost for disposal is just so expensive. Most of our clients, even though they're facilities that are non-hazardous waste landfills that you can send.
We lost them.
Oh, thank you. Although there's, much better. Although there's many landfills that are subtitle D landfills that are taking PFAS, most of our clients are really concerned with the, issues of sending soil to a subtitle D landfill and are preferencing sending them to hazardous waste landfills at extreme cost. So our clients are very protective of that, and they're liking this technology as a way to remove the leachability hazard. We run SPLP on the back end of it to show it's not leaching anymore, so it's not going to be an issue going to a landfill. And then destruction of the super concentrate mass.
Any other questions?
All right, well, wonderful. Everybody give a round of applause for our session. All right, we're going to break for the next 30 minutes. Go visit the exhibitors, get a cup of coffee, and then come on back and we'll wrap this up. Is Dan Nelson and Emily Harper in the room?
It's quarterly.
Yeah.
Once they hit
Okay.
it cuts it down to bi-yearly, and then once they hit 2 to 4 non-detects, then they're yearly.
Yeah, and then if they hit it, get a hit.
You can't do that.
It's all based on.
It's good.
And you didn't put all your weight. Okay, good, good, good.
That's under review.
Yes.